You are 400 kilometers above the Earth, sealed inside an orbiting metal tube, when the alarms trigger. The system responsible for producing the air you breathe has just failed. Every single day, a human body requires about 0.8 kilograms of oxygen to stay alive. Without a steady supply of it, the brain begins to suffer permanent damage within minutes. During the Apollo era, meeting this biological baseline was relatively simple. Because lunar missions lasted only a few days, astronauts simply packed enough high-pressure oxygen tanks into their landing modules to last the round trip. But the International Space Station presents a completely different logistical reality. It has been continuously inhabited by humans for more than 2 decades. You cannot launch a 25-year supply of compressed air on rockets. Instead of treating the station like a vehicle that carries its supplies, engineers had to design it as a mechanical, miniaturized Earth, capable of continuously reclaiming and regenerating the very air its crew breathes. Looking at this internal schematic of the space station, we can map the primary life support loop. Aboard the ISS, every single drop of moisture, from exhaled water vapor to shower runoff and even urine, is captured and reclaimed by the environmental control systems. This purified water is then fed into a device called an electrolyzer. By running an electrical current from the station's solar panels through the water, the machine physically splits the H2O molecules into 2 distinct gases, hydrogen and oxygen. Down on Earth, the newly formed oxygen bubbles would naturally float to the surface, but in continuous freefall, there is no buoyancy. The bubbles stubbornly cling to the metal electrodes. To detach them, the station pumps the frothy water into a mechanical centrifuge, spinning it rapidly to force the gas and liquid apart. This process frees the oxygen for the cabin, but it leaves behind highly flammable hydrogen gas. To safely dispose of this, the system feeds hydrogen and exhaled carbon dioxide into a Sabatier reactor. Inside the 750-degree heat, chemical bonds break and reform, producing methane that vents into space, and brand new water routed back to the electrolyzer. It is a chemical marvel that recovers the majority of the station's vital elements. But the process relies heavily on fast-spinning centrifuges and dozens of complex moving parts, hardware that constantly fights friction and is vulnerable to mechanical failure. When those moving parts do fail, or the station temporarily loses power, the astronauts can't simply open a window. The entire primary system shuts off, and the air immediately begins to stale. The immediate failsafe relies on the Nitrogen Oxygen Resupply System, or NORS. These are heavily armored, high-pressure tanks plumbed directly into the station's airlock, waiting in reserve. But these tanks represent a severed loop. They have to be physically hauled up from Earth on automated cargo ships. When a module docks, it pumps fresh gas into the reserves to keep the station breathing. Having cargo ships top off your air supply is an excellent safety net when you are in low Earth orbit, but it strictly tethers human survival to a tightly scheduled, multi-million-dollar logistics chain. It is a lifeline that cannot stretch to deep space. So what happens if the primary electrolyzer is broken, and a delay on the launch pad means the resupply tanks run completely dry? The final option is a system called a solid-fuel oxygen generator, commonly known as an oxygen candle. It is a chemical canister packed with solid lithium perchlorate. When ignited at 1100 degrees Fahrenheit, the block burns, releasing enough breathable oxygen to keep one crew member alive for a single day. In 1997, the crew of the aging Russian space station Mir found themselves relying on these exact chemical candles. On a routine day, an astronaut struck the ignition mechanism, but a microscopic fragment of latex glove contaminated the canister. Instead of a slow release, the candle erupted into a blinding, unextinguishable blowtorch. Fighting a roaring fire inside a cramped, smoke-filled aluminum tube orbiting the Earth is one of the most perilous situations imaginable. The flames consumed the very oxygen the candle was meant to produce, while filling the module with thick, toxic smoke. When primary machines and secondary tanks fail, the remaining failsafe is a chemical reaction burning at 1100 degrees. In the void, the difference between a life support system and an unquenchable fire can be a single microscopic contaminant. If we attempt a 3-year mission to Mars using this architecture, we will fail. Mechanical centrifuges will jam, supply rockets will not be able to reach the crew, and lighting chemical fires millions of miles from home is a death sentence. Engineers are now testing an experimental technology called the Magneto-Hydrodynamic Oxygen Generation Assembly, or MOGA. MOGA eliminates the need to spin water. Instead, it uses the Lorentz force, deploying magnetic fields to pull oxygen bubbles from the electrodes in a straight line. Replacing physical pumps with invisible fields means zero friction and virtually no moving parts. Building life support systems with this level of mechanical simplicity addresses one of the most critical points of failure for a mission to Mars. By mastering the ability to pull air from water using nothing but invisible forces, humanity is learning to pack the breath of our home planet into our pockets, carrying it as we step permanently into the dark.